you recall last week, we did investigations and explorations on exponential functions. The general form for an exponential function was written f of x, or y, equals a times b to the x. B is the base, x is the exponent. We noticed last week that if b was a value greater than 1, it represented exponential growth, as depicted in this graph. If the value of b was a proper fraction between 0 and 1, then this represented exponential decay, as depicted in the graph. So you should be able to look at an equation and determine whether it represents exponential growth or decay based on the value of b. So if we look at this example, we can take the parent function y equals 2 to the x. Now, as we saw, the domain for an exponential function is negative infinity to positive infinity. So we write this as all real numbers. The range for this growth function, parent function, y equals 2 to the x, is 0 to infinity, not including 0, because as we discussed, there was a horizontal asymptote at y equals 0, the x-axis. So if we substituted in values for x into the function, when x is equal to 0, the function value output is 1. When x is equal to 1, the function value is 2. When x is equal to 2, 2 squared is 4. 2 to the third power is 8. So we can see these points being plotted on the graph. Now notice, as the x values decrease, the graph of the functions gets closer and closer to that horizontal asymptote, the x-axis, but it never touches it. In this case, the x-axis is an asymptote, as you may recall. Now, if we continue, so if you are given an equation, an exponential function, can you determine if it is strictly increasing or strictly decreasing, or neither? So in the case of it strictly increasing, b is greater than 1. Strictly decreasing, b is in between 0 and 1. So the function values, the output values, in this case, f of x1 is greater than f of x2, so that should make sense. Strictly decreasing, f of x1 is greater than f of x2. So we should recall those definitions. So if we look at the first one, we see that the base is 2. Since the base is equal to 2, that's a value greater than 1, so it's strictly increasing. In the second example, we see that the base is a half, so this is strictly decreasing. And you could graph it to verify. So how do you go about graphing exponential functions? Well, first state whether it represents exponential growth or decay, and then sketch a graph. So if you recall, when we had the general form of an exponential function, b was the base, and a represented the y value of the y-intercept. So the base told us whether it was growth or decay, and the a value told us where the graph crosses the y-axis. So in the first example, you see that b is between 0 and 1. This implies that we are dealing with exponential decay. Now the a value is equal to 10, so we know that the y-intercept is 0, 10. So to sketch a graph of this exponential function, plot the y-intercept and demonstrate that you are dealing with exponential decay. In the next example, you see that b is greater than 1. So this implies that we're dealing with exponential growth. Now, what is the value of a? Well, it's not explicitly written, but we know it to be 1. So a is equal to 1. So this exponential function is going to have a y-intercept of 0, 1. So if I wanted to sketch a graph of this function, again, plot the y-intercept and show that it's exponential growth. Again, we should keep in mind there is a horizontal asymptote on the x-axis because there's no transformation shifting this exponential function up or down. Now looking at the next example, we see that b is greater than 1, so again this implies exponential growth. The value of a is 5, so the y-intercept is 0, 5. So to sketch a graph of this exponential growth function, again, plot the y-intercept and just demonstrate that this is exponential growth. Now, if we were trying to, and show the horizontal asymptote, if you were trying to graph this a little bit more precisely, we would have to complete a table of values. And we could do that, but since this is just a sketch, this is sufficient. Now, what if I give you a function, an exponential function? Again, in this case, we could identify pieces of this to give us some information, like this would tell us that it's decay. This would tell us our initial y-intercept, but then you should notice that you have transformed, you have vertically shifted this exponential function down 1. So you could plot points and you could identify information about this, but perhaps we would want to see how we would evaluate this using a calculator. So you would put this equation into the calculator, into y equals. So y equals, put that in your calculator, and then go to your table of values and look for when x is equal to -5. You should do this activity and see if you can actually get these values. So again, put the exponential function into y equals, then go to table, second graph, and scroll down until you look for the x value that is -5. What is the corresponding y value? You should be able to get 14.954. Do the same thing using the same equation, looking at your table of values, and now look for when x is equal to 0. What is the corresponding y value? You should be able to get 12.49. And lastly, repeat the exercise, but now looking for when x is equal to 5. What is the corresponding y value? 10,000, or 10.406 rather. Now, just as we've graphed parent functions in the past and been able to identify transformations made to the parent functions, we're doing the same thing here, but now with an exponential function. So, if you're given this function g of x, what is the underlying parent function? Well, you should be able to recognize that the parent function is y equal 2 to the x. Then you should notice this -2 is a transformation, a vertical shift down 2. So we could make a table of values and show each step, or you could pick x values, substitute into the original function, and find corresponding y values. But let's say we want to go ahead and do it with the original parent function. Let's say we choose x equal to -2 and 0 and 1. We know the domain is all real numbers, so we could really choose any x value. But let's think about the y-intercept and other values. For x equal -2, 2 to the x, y is 1/4. For x equals 0, 2 to the 0 is 1. And for x equal 1, 2 to the x is 2. So I could plot those points, -2, 1/4, 0, 1, 1, 2. I know this is exponential growth. There's my parent function. Now, I know currently my horizontal asymptote is at the x-axis, y equals 0. But this has been transformed, 2 units down. So if I were to subtract 2 from each of these? Well, I could actually take each point and subtract 2 from that y value, or I could take each of these points and shift them vertically down 2. So here is our transformed function. We took our parent and we shifted it 2 units down. So hopefully you can recognize that you have a new horizontal asymptote. Where is it? Y equals -2. And we can see that in the equation from the vertical shift down 2. So what is the domain of this function? Well, it's still all real numbers. What is the range of this function? Well, now it's -2 to infinity because we've shifted it down 2. And the horizontal asymptote is at y equals -2. Now let's look at the next example. The next example, can we identify the transformations that have been made? Well, in this case, we see that there are 2 transformations. We have this -5 and we have this +4. Now, do you recall what those transformations represent? Maybe thinking back to other types of functions and how we recognize those transformations. Well, this -5, hopefully you can recognize as a horizontal shift right 5 units. And then this +4 represents a vertical shift up 4 units. So this is very similar to what we've done in the past with the transformations. So we could plot the original function, y equal 2 to the x. We know this information from the previous example. And we know what type of transformations are happening. We are shifting 5 units to the right. So I could take this point and shift it 1, 2, 3, 4, 5 units to the right. I could take each of those and shift them 5 units to the right. And then I would apply the other transformation and shift them 4 units up. So here is my image function after applying both transformations. So what is the domain and the range and the horizontal asymptote of my image function? So the image function, the result of applying 2 transformations. So if I'm looking at my image function, I have my domain as all real numbers. I have my range. Well, what have we done? Moved it up 4. So now that's 4 to positive infinity, not including 4 because we have a horizontal asymptote at y equals 4. Now we explored the natural number e, which was developed by the Swiss mathematician Leonhard Euler. Now Euler, the number e is a very important number like pi and I. It's most interesting is how it's defined. Where did it come from? How do you generate e, the values of e? Well, if you take this expression, 1 plus 1 over n to the all raised to the n power, look at what happens as n gets larger and larger. Well, when n is 1, we just have 2. If we let n equal 2, notice how we're increasing the values of e. So therefore, we can see e, and we'll notice that e will be used for a natural base. So if you recall, we looked at what happens when we had y equal e to the x, the natural exponential function. Most people just use an approximation 2.71. Now I want you to use your calculator again, and I want to see if you can evaluate different values of y equal e to the x. So go ahead and put, y equal e to the x into your calculator. And then look at your table of values for when x is equal to -5, when x is equal to 0, when x is equal to 5. If you look at those values, you should be able to see that e to the -5th power is 0.0067, e to the 0 power we know is 1, and e to the 5th power is 148.41. Okay, let's look at an application. Exponential functions are used a lot when dealing with population growth or decay. If you look at how populations respond to disease or other things or predators prey, you use exponential growth and decay models. Another very important application of exponential functions is money, due to growth of interest received or depreciation due to interest owed. So if you buy a house or you invest money or you buy a car, you'll see these interest formula. So for example, let's say you have some interest that you're compounding. You invest some money. Well, in this formula, the P stands for your principal. This is the initial amount, either the initial amount that you start off owing or the initial amount that you invest. The R in the formula is going to be the annual percentage rate. Maybe you've heard APR. N defines the number of compoundings per year. So if a problem says that the interest is compounding annually, N would be 1 in the formula. Semi-annually, N would be 2 in the formula. Quarterly, N would be 4. Monthly, N would be 12. Daily, N would be 365. So you may be told at what percentage rate your interest is being compounded and how often it's being compounded. Now, what does the T stand for? Well, you should be able to guess. That's what? The number of years of the investment, the time, number of years of investment, of compounding. A is the output, A of T, the accumulated value of the investment. So if we are compounding annually, let's look at what the formula would look like. P times 1 plus whatever the rate is. Well, annually, N would be 1. So it would look like this. Now, let's look at an example. A city population, which was initially 15,500, has been dropping 3% a year. Let's say we want to write an exponential function and graph it, and then use the graph or the table of values to predict when the population will drop below 8,000. So let's see. What information do we have? We have the initial population. What is that going to be representing? Well, that P. It's also can be seen in formulas as a little lowercase a. It depends. In certain industries, they use P for finance. They use A when you're dealing with medical or biological examples. So let's see. We have A of T equals the initial amount, 5,500. So this would be little a or big P. Now it's been dropping. So dropping implies that it's minus. So this formula is plus if we're adding an amount, but since we're dropping, it will be minus. Now, what is percent? 3% as a decimal would be 0.03. And it's happening yearly, annually. So the N is going to equal 1. So how would we answer this question? Well, we could put this into the calculator into y equals. And change that unknown independent variable t to an x. Once you enter this equation in the calculator, look at the table. Now, what are we looking for in the table? We're looking for when the population will drop below 8,000. So find in the table where the population reaches 8,000. You should be able to determine that's at x equal 300. So that's t equal 300. So if we look at that, oh, I'm sorry. I jumped ahead at the previous problem. Let's go back. That's not correct. I take that back. I jumped up ahead. It's not 300. I answered the next question. So again, we have this equation in the calculator. We're looking at our table of values for the corresponding x for when y is 8,000. You should be able to see that the population will drop below 8,000 between 21 and 22 years. Now, the next part of the problem is asking what will the population be in 300 years? So now I'm actually looking for when x is equal to 300. So what am I doing? I'm using the same formula, but now I know t. So I can just look for when t, or x, is equal to 300. Replace the x with 300. And what are you going to get? How many people will be left? Well, if I evaluate this, I'm going to get 1.667. Now, since these are people, you have to round down. You can't have fractional parts of people. So there will be one person left in 300 years. Now, we talked about how to use compound interest formula for when you have an annual percentage rate that's being compounded a specific number of times per year. But what happens when you have it compounding continuously? So this is the equation for compounding continuously. So if your word problem says that it's being compounded continuously, you're going to use the PERT formula. So the final amount will be equal to the initial amount, P, times e to the RT, where again, R is the rate, T is the time. So let's say Mary's parents deposited $10,000 in an account that pays 7% interest, compounding continuously. If you were to read that type of a word problem on a quiz or a test, you should know immediately that you're dealing with the PERT formula. So let's substitute in what we know. P, the initial amount, is 10,000 times e to the rate of 0.07, since it was 7%, t. Now the question is asking, after 18 years, Mary withdraws all the money to start paying for college. How much money does Mary have? Well, at this point, we are looking for the function evaluated at t equals 18. So we just substitute in 18 in for t, and if we evaluate that, you should be able to get $35,254.21. Now, since this is dealing with money, in a word problem, you want to make sure that you have the cents included. So let's say you have $12,000 to invest, and you're going to invest it for 3 years. Which of these options is going to give you a greater return over 3 years? If that $12,000 is compounded monthly, in which case we would use the formula, this one, which would be principal times 1 plus rate 0.07 monthly, and would be 12, and then 12 times 3. Or if we had the same amount of money compounded continuously at a different rate. So again, since it's compounded continuously, we'd use the PERT formula. $12,000 is your initial amount times e to the rate, in this case 0.0685, times the same amount of time, 3 years. So you're given two options and you're trying to determine which investment yields a greater return over the 3 years. You tell me, which one, where would you invest your money? Actually figure it out. Pause the video and determine which one you would use. Hopefully, you're able to recognize that with your first option, you would have 14,798. In the second option, you would have $14,737. So hopefully, you'd go with the first option.